Solve for x. In this chapter, we reviewed some techniques for solving equations, including rewriting chunks of the equation with things that are equivalent to what was in there, using the idea of undoing operations to get things away from my variable x. Um, also, the ideas of our properties of equality. If I have equal quantities and I do the same thing on each side of that equality, I get an equivalent equation that has all the same solutions. Also, in this chapter, there were some newer ideas, right? One of them being this idea of looking inside an expression, looking inside of something and seeing what that has to be to make something true, looking inside fraction busters, and also the idea of sometimes, like for the exponential equation, rewriting the bases, but that's still just rewriting. So let's take a look at A. So in part A of this three-part question, we're asked to solve this equation. And when I look at it, I can see, I'm taking the square root of something. I'm taking the square root of this expression, 3x plus 9. And when I take the square root of that expression, I'm getting an answer of 6. So because I understand squaring and square root, right? Squaring and square root, I could look at a couple perfect squares, like 2 squared. I didn't mean that to be green. I could look at, for example, 2 squared, and I can see, oh, that's the number 4. 3 squared, that's the number 9. 4 squared, that's the number 16. 5 squared is the number 25. And 6 squared is that's 2 to the 6th power, Mr. Roberts. 6 squared is the number 36. So this pattern continues. And I can see here a bridge between perfect squares and square roots, right? Or perfect squares and square roots. So if I was to go the other way, I could say, look, the square root of 36 gives me 6. The square root of 25 gives me the value 5. So if I'm looking at this and I'm like, hey, I don't know what I take the square root of to get the answer of 6, I can just think, well, let me just square that in my mind, right? If I square 6 mentally, 6 times 6 is 36. So what that tells me is that this thing, this expression that lives inside of the radical, must be the number 36. Well, if that's the case, right, I can simply set it equal to 36, and that will allow me to find the value of x that makes it become 36. So if I take away 9 from both sides, we get that 3x is 27. And if I divide both sides by 3, I get that x is 9. So what we're saying here is when x is the number 9, the expression 3x plus 9 is 36. And that's what we want because the square root of that expression is supposed to give me an answer of 6. So of course we can check that by just grabbing this value of 9 right there and placing it in for x. When I place 9 in for x, 3 times that 9 gives me 27. 27 plus 9 gives me 36. And you can see, yeah, now that that's 36, I've got the square root. The square root of it, of 36, is 6, which is exactly what it was supposed to be on the other side of the equation. So when x is 9, the expression becomes 36, and the square root of that expression is supposed to equal 6, and it does. For part B, this is a good example of sometimes it's useful to rewrite things. When I look at the number 9 and 3, I'm thinking of a base of 3, and it's kind of useful to just kind of jot down some examples of base of 3. So I might write down 3 to the 0, 3 to the first, 3 to the second, 3 to the third. I can go on a long ways. 3 to the, I didn't write third, I wrote 3 to the second twice, 3 to the third, 3 to the fourth. Also, I can go in the opposite direction. So past the 0, right, 3 to the 0, I could have 3 to the negative 1 or 3 to the negative second, for example. If I start with 3 to the first, I know that 3 to the first is is the number 3. 3 squared is 3 times 3, which is 9. 3 to the third is 3 times 3, which is 9 times 3, which is 27. So as I go down this list, I just multiply my previous term times another 3, and I get the new term, right? 3 times 3 gives me 9. 9 times 3 gives me 27. 27 times 3 gives me 81. And I can also go backwards on this list by instead of by multiplying by 3, right? I can undo that multiplication by 3 and go backwards on the list by simply dividing by 3. 81 divided by 3 is 27. 27 divided by 3 is 9. 9 divided by 3 is 3. 3 divided by 3 is 1, which is a great bit of evidence why we think that anything to the 0 power is the number 1, right? I can just see as I followed that pattern, I landed at 1. Now let's take the number 1 and divide it by 3. 1 divided by 3 is 1/3, right? It is 0.3333 if you look at your calculator, but I'm just putting a factor of 3 in the denominator, right? Each time I divide by 3, I put another 3 in the denominator. And in fact, 3 to the negative second, that's 1 over 2 factors of 3 in the denominator. It's 1 over 3 squared. Well, 3 squared is 9, so this is 1/9 and 1/3. Well, so for this problem, I can see that I have the number 9, right? And I also see that I have the number 3. Well, 3 is great. It's already on this list, so I'm not going to change that. I'm going to leave it. But the number 9, instead of writing as 9, oops, let me use the orange. Instead of writing the number 9 as 9, I'm going to write the number 9 as 3 squared. So this is an example of rewriting. I'm going to rewrite the left-hand side as 3 squared, but I'm still raising that to the x minus 7 power. And over on the other side, it's 3 raised to the x minus 1 power. Well, that's cool. That's that's cool because now I can use this power rule where I'm raising a power, second power, to the x minus 2 power. And in order to raise 3 to the second to the x minus 2 power, I just multiply these. And we've seen a lot of examples of that. So I can rewrite this as this base is 3, but I'm going to be raising it to the 2 times x, which is 2x, and then 2 times negative 7, which is negative 14 power. So this thing that I've written here, this 2x minus 14, is exactly what I get when I multiply 2 times x minus 7. On the other side, I didn't change anything. It's just still 3 to the x minus 1. What's nice is at this point, we can look at it. We could say, this is really cool. This is cool. The only way that these two quantities can be equal to each other is if their exponents are equal to each other. So what I can do is I can say, well, let's just make this exponent, right, equal to the other exponent. I'm going to set those two equal to each other. The exponent that I've highlighted in green equal to the exponent that I've highlighted in purple. And then when I do that, I can solve by, I guess, taking away an x from each side. And then I can solve by adding 14 to both sides. So I would get that this would be a positive 13 is the value of x. So there it is. When x is 13, these two expressions are apparently equal to each other. And in fact, I'm going to check that with a pretty straightforward little calculator here. So I've got on the one side 3 to the x minus 1. So I'm just going to go 3, and then I'm going to raise that to the power of, oh, no, now why did I hit 33? That's not what I wanted. 3 raised to the power of, and then in parentheses, I'm going to go 13 minus 1. So 13 minus 1. And then close the parentheses. So 3 to the 12th power is a large number. But then let's do the same thing on the other side. So on the other side, I'm going to have 9, and I'm going to raise 9 to the 13 minus 7 power. So I'll open parens. 13 minus 7 power, close parens. And I get another large number, but where'd it go? Oh, there it is. There's my history. So you can see both of those are exactly 531,441. So when x is 13, it does make the left and the right hand side the same. And then for the final part, for question 3, this is an example of a wonderful opportunity to use fraction busters. So what we are going to do here is we're going to multiply both the left and the right hand side by a fraction with the numerator or denominator of 1, but with a numerator that's built on the values that I see in my denominators. So you can see there's a factor of x living in one of the denominators and a factor of 3 living in the other denominator. So I can multiply both sides, or every single term in this equation, by 3x, right? I'm going to include a factor of 3, and I'm going to include a factor of x. And when I do that, all those fractions are just going to go away. So let's look how I write this. My next step, I'm going to go 6, and then I'm going to make room for some new factors over x, plus 1. I'm going to put some new factors in there as well. And then equals 5. Some new factors are coming in over 3. So in every single place, I'm going to write a times 3x, a times 3x, a times 3x. So if we look very closely, we can see that this first term got factors of 3x. The second term on the left-hand side got a factor of 3x, factors of 3x. And then the right-hand side got 3x. So that factor of 3x was pushed across the entire expression. What's nice about that is I've identified some values of 1 as a result. So this, right, x over x is equal to 1. So this becomes just the number 18 plus 1 over 1 is 1. This is just going to be 3x. And then equals, this has a giant one in the form of 3 over 3, so this is going to become 5x. If I subtract 3x from both sides, we get that 18 is 2x. And if I divide both sides by 2, we get that 9, right, is what x is. X must equal the number 9. Again, that's a fairly straightforward expression to check. In fact, I think I'll try it with my calculator. Let me grab the calculator, and I'll put it over to this side. So I think x is 9, so I'm going to clear everything. And I'm just going to go 6 divided by the number 9 plus 1. And you can see I get this answer, 1.666666. And if I look at that, pretty sure that's 5/3. If I go 5 divided by 3, you can see I get the exact same decimal. So yes, when x is 9, both sides of that equation become 5/3 or 1 2/3.